to you about CM theory via p-adic deformations, which is already subtly hinted at during Jan's talk, that sometimes you can use deformation theory for ordinary p-adic modular forms. And to motivate the work that I will talk today about, I would like to recall singular moduli, which are the CM values of the J function. In other words, they are the J invariants of elliptic curves with complex multiplication. Here I wrote down a couple of rational ones, so you can see that these numbers are very smooth. And what is a little bit less known is that if you take the difference of two of these numbers, then somehow they're still very smooth. And this was, I mean, if you believe the ABC conjecture, then this shouldn't happen in general. But still it's true, and in fact it was proved and explained by Gross and Zage in the 1980s that if I take any two of the CM values of the J function, then not only can I show that these primes are all sufficiently small, I can also show that I can even prove an explicit prime factorization formula. And in short, Zage, he gave a beautiful proof in his paper, and it can be condensed to this one-line proof, but I understand that maybe this is not the most insightful at this time, so let me expand this a little bit. And yeah, it can be roughly divided into three steps. So the first step is to write down some kind of family of Hilbert modular forms for this real quadratic field F, given by the product of the two negative discriminants, which is then positive. And it is a parallel weight 1, 1, and it has the property that if I specialize the s equals 0, then I vanish. And then I apply a couple of operations. So I take a diagonal restriction, which just means I plug in z1 equals z2. I take the derivative with respect to s, and then I apply something called the holomorphic projection operator. And then, after I've done all this, I land in weight 1 plus 1 equals 2. I have no level, I am holomorphic, and therefore I am 0. And then we are done if we equate the Fourier coefficients of this monstrosity to 0. And why are we done? Because these Fourier coefficients actually look like the logarithm of the norm of the difference between these J invariants minus the logarithm of some kind of explicit factorization. So if this is to be 0, then these things better be equal. So it's a really magical proof, but it's really nice. And today we'd like to talk about a p-adic analog of this proof. So let's get started. So first we have to view our Eisenstein series as a p-adic modular form, so I have to p-stabilize it in some way. And I choose my prime in such a way that it splits in F. So I have two primes to work with, and I choose opposite signs for this p-stabilization. So then I get for the constant terms of kind of cancellation, and I actually get a p-adic cusp form. And then I can actually try to find a family not of Eisenstein series passing through this guy, but even of cusp forms passing through this guy. And then I try to run the same argument as before. But I mean, writing down one cusp form is difficult enough, let alone like a whole family of these guys. So how do you actually do this in practice? Well, it turns out, as you might know, that the Galois representation associated with an Eisenstein series is very simple. It's just the sum, in this case, two characters. I didn't tell you quite what chi is, but it's just a character. And now the deformation theory comes in when I say, well, what I actually want to do is I want to deform this Galois representation a little bit, infinitesimally. You can just write down these deformations completely explicitly. And then I want to argue that these deformations, which are just Galois representations, absolute Galois representations at this point, they actually come from modular forms. And I have to prove something called an R equals T theorem. But after I have this, I can compute traces of Frobenius, and I can get some Fourier coefficients back. And then this epsilon part is actually the derivative that I'm looking for. And then I can run the computation and see what comes out. And this deformation theory approach is inspired by, of course, the proof by Zage, also work of Damon, Lauder, and Roger, and more recently also work of Damon, Otzi, and Vonk, who applied this not in the CM setting but the RM setting. And now I've given you the proof, but I haven't yet stated the theorem. So let me get to that. And in order to state the theorem, I need to introduce p-adic theta functions. And the p-adic theta functions I would like to look at today are given by choosing two base points in the p-adic upper half plane. And if I have a maximal order in a definite quaternion algebra, I write down this infinite product over all the norm 1 elements in this maximal order after I invert p. So this is just some kind of infinite product. And it turns out that in the variable z, which is the variable of the function, it's almost invariant under the action of the group. Not quite. There's in general some automorphic factor, but we can actually do some tricks and get around this. We can take some kind of cross ratio that is that somehow lets this guy drop out. So the p-adic theta function that I want to choose is supported at two base points, which are two CM points, the CM point and its Galois conjugate. And then I will evaluate this theta function at a different CM point and its Galois conjugate. And I get this somehow infinite product of cross ratios, which is just a number, p-adic number. And now you can put it in a computer and see what comes out. And if you do, for example, for discriminant minus 43, minus 163, you'll find this Gros-Aguet style factorization of the norm. And this was what my theorem was about. And the reason why we care about being able to compute these kinds of infinite p-adic products, not just because it's nice to be able to generate, to generalize the results by Gros and Aguet, but also because it's connected to something which has been cropping up recently, which is the theory of rigid meromorphic cocycles. So in a paper a few years ago, de Mon and Vonk, they constructed a p-adic analog of these differences of singular moduli that we've been studying, but not for imaginary quadratic fields, so not for CM theory, but actually for RM theory, so for real fields. And the main conceptual step somehow is that this J function is a function invariant in SL2Z, so it naturally lives in some kind of H0. But these rigid meromorphic cocycles, which I cannot define due to time constraints, they somehow live in an H1. So they go up 1 degree in cohomology. And to give you just the faintest hint at the key idea to construct these guys is that somehow you use Archimedean information to cut out finite sets, and you use these finite sets to construct p-adic products that converge. So somehow there's some interplay between the infinite place on the upper half plane and the p-adic place on the p-adic upper half. Now, this has been generalized recently to quite some extent, without going too much into detail, but it's now known that if I take a quadratic space of signature Rs, then I have an Archimedean space and a p-adic space, and I have a notion now of rigid meromorphic cocycles that actually live in the HS, so they're S cocycles, where S is the negative definite part of this quadratic space. And then I also have a notion of special points where I can evaluate these cocycles, and they give rise to arithmetically interesting infinite p-adic products that you can try to compute, and conjecturally they're related to explicit class field theory in Hilbert's 12th problem. The Von case comes from signature 2-1, and this explains why they find 1 cocycles. But somehow this seems to skip the easiest case, which should be S equals 0. And indeed, if you do S equals 0, then you find these p-adic theta functions as natural rigid meromorphic cocycles, because they're maybe up to this automorphic factor that you have to cancel out. They're like gamma invariant functions. And the Archimedean input that was hidden on the previous slide is actually that this quaternion algebra that we started with is definite, which is something that happens at infinity. But it has this property, or this is as a consequence, that the number of quaternions with a fixed norm is actually finite. And this is the thing that will make this infinite p-adic product that I wrote down on the previous slide converge. So somehow you see in a very hidden way that this interplay between infinity and the p-adic place. So the thing that I proved, as I announced, was that the CM values of these guys, they have a Gros-Aguet style prime factorization. And now what's most exciting about this, not just the relation with rigid meromorphic cocycles, but also that you can interpret the CM theory back in the classical setting. And now it turns out that if you take a Shimura curve, and there's a p-adic uniformization, which actually says that the Shimura curve associated with some indefinite quaternion algebra is actually over the p-adic numbers looks very much like this product where these theta functions are supposed to live. So these norms of the CM values of the theta function, you can directly translate this result to the norms of CM values of modular functions on Shimura curves. So you get results of the complex numbers back using this p-adic approach. And the main consequence, the last thing I will say, the main power of this p-adic approach is that it, unlike the classical methods of the complex numbers, naturally seems to allow you to refine these results beyond computing just norms, like Gros and Aguet did. Namely, this 1 plus chi is the induction of the trivial character, which morally corresponds to summing together all the Galois conjugates, so you get the norm. But if you induce a non-trivial character, then you morally expect to compute a kind of character-weighted sum of all the Galois conjugates. If you then apply a reverse Fourier transform, you can get your hands on one of these Galois cones. It's an actual expression for the CM value of this modular function, which you prove in this p-adic way that you can make sense of over the complex numbers. So this is, to me, very exciting, that you can refine classical CM theory in this way. And this is ongoing work with Ying-Kun Lee, of course. And yeah, I hope to be able to report concrete results to you the next time we meet each other. So thank you for your attention.